So I want to take a quick detour and talk about projections, but I need to give two disclaimers. The first disclaimer is this is review. So if you already are pretty comfortable with projections, go ahead and skip the segment. The second disclaimer is, yes, I'm giving a little bit of review of a linear algebra topic, but that doesn't mean I'm going to be able to do that for every linear algebra topic. So there are lots of things in this course that you just need to know from your previous course, or we can talk in the office hours. So don't necessarily think that you're going to get review of every other linear algebra thing that comes up. The reason I want to talk about this one is there's a sort of geometric interpretation that maybe you didn't see before. So I want to make sure we get to that. The reason that I'm going to care about projections is later in the lecture we'll see a case where I'm talking about a linear program. I'm talking about its feasible region. So let's say it's this, and I'm standing on the boundary. And I'm asking a question like, can I improve this solution? Can I find a larger value of the objective function? And I look at the gradient of the objective function and it points this way. And I think, well, yeah, if I'm standing here and I walk in this direction, I can improve the objective value. But I'm not allowed to because I'm standing on the boundary. I can't leave the feasible region. On the other hand, if I walk along the boundary a little bit this way, I will improve the value a little bit. And so, of course, what I need to learn is how do I find a way of hugging the boundary? How do I stay on the boundary and still walk broadly speaking, in the direction that I want. And that's where projections come into it. The notation that we use for a projection, the projection of V onto U is this. Although, to be honest, I don't find myself using that notation often. I find myself talking about projections a lot, but I often don't use the notation. We often want to talk about projections because we are working with some other algebra and we want to observe that a particular term inside of an equation corresponds to a particular projection. Okay, so what's a projection intuitively? Well, suppose that U, this vector U, is parallel to that boundary, and I have to hug the boundary. So I'm only allowed to walk in direction U. The best intuitive description I've heard of what a projection is that if U is the ground, if U points along the ground, V, this projection of V onto U would be the shadow that V casts onto the ground. So the shadow that it casts onto U. So I just drop directly down to the direction that I'm allowed to use, the direction U. Formally, what you could also describe the projection as is, so here, this vector here would be the projection. Formally, the projection is the best approximation of the vector V using only the direction U. So it's the best approximation I can come up with for my vector V in that direction. This is the formula for it, which, I mean, sort of appears out of nowhere. And I think I should justify the formula just a little bit, but I'm going to do that in reverse because there's a special case that I think makes a little bit more sense. So suppose that U is a unit vector. So in other words, it's a vector we're keeping around for the sole purpose of representing a direction. Its length is irrelevant to us, so we've made it a unit vector. You might remember that the dot product, if you have a unit vector, this dot product V dot U will be the scalar, I guess you could call it the length of the projection, the component of V in the direction of U. But what I want when I ask for the projection vector isn't just a length, it's a vector. And so what I want is a vector that is the same direction as U, but with this length. And that's pretty easy if U is a unit vector. So I know that the length of U is 1, and so the length of U times V dot U, so V dot U is a scalar, the length of U times V dot U will just be whatever the value of V dot U was. So if U is a unit vector, then this does give me the projection vector that I was looking for. I'm just multiplying my unit vector U, which is the direction that I want, by the length that I want. Okay, so how does that apply if U isn't a unit vector? Well, what we can do is basically sub in to this equation the situation where U is some arbitrary vector. So, for example, consider consider W in Rn. And suppose that we don't know anything about the length of W. Well, what I want is the projection of, if I want the projection of V onto W, so I want to project onto W my vector V, then I want to use this formula. But I can't because W isn't a unit vector. So I could always make W into a unit vector. Well, how do I do that? Well, to make W a unit vector, I divide it by its own length, because that way the length of the result will definitely be 1. So I say, well, why don't I just sub in this term here, W divided by length W. Why don't I just sub that in to this formula everywhere I'm using my unit vector u? Okay, so we do that. So the projection of v onto w would be w divided by length w multiplied by v dot, and then again w divided by length w. And if I work that out a bit, what I end up with is w. What I'm going to do is these scalars, these scalar length, I'm going to just pull them out of the equation. I end up with w times v dot w all over the length of w squared. So it's squared because I get it from here and I get it from here. You might remember that the length of a vector squared would just be the vector dot product itself, which is the same. If we look at the resulting equation, that is this formula from the previous slide. So really what I've done is I've leveraged this property of dot products and then just worked backwards from there to apply it to arbitrary directions. So the vector I'm projecting onto isn't necessarily a unit vector. One of the reasons this is significant is that I can use projections to solve this other problem that I often have, which is I have two vectors, a vector v and this vector u, which is meant to represent some direction, and I assume therefore u is non-zero. I have these vectors. Often what I want to do is I want to work out the component of v in the direction of u and the component of v orthogonal to u. And I always can create such a decomposition. I can break up any vector v into two pieces, one that is parallel to u and one that is perpendicular. And the way that I do that is I just choose the parallel component can be the projection. I just project v onto u. And then the perpendicular component I can compute by taking v and just subtracting off that parallel component. And it turns out that you're guaranteed that this quantity will be perpendicular to u. I can give a quick justification. The only reason it wouldn't be perpendicular to u would be that this projection v sub u doesn't quite line up directly underneath v, I guess, for lack of a better term. So for example, if the projection only came to here, the resulting vector v minus vu would have some component in the direction of v. If the vector came all the way out here, the resulting v minus vu would have some component in the direction of u as well. And because we know that the projection is the best approximation in the direction of u, we should expect that there should be no way I can move in either direction that would get me closer to v. So the only way to get from here to v is traveling in the exact orthogonal direction to the direction u that I'm allowed to use. So as a result, we actually can compute this decomposition. We just take the parallel component to be the projection and the perpendicular component to be everything else. And then to just carry us back to this discussion of lines and normal vectors. So I mentioned before that normal vectors are a great way of characterizing a line. It turns out they can characterize an n-1 dimensional subspace of any number of dimensions, which is one reason we like them. In 2 dimensions, it's not as obvious how important normal vectors are, because we'll see even in this example that it looks sort of like a vector that looks like this could be used instead, a vector parallel to my line. But I'll walk through the example and then explain why normal vectors are still great. So suppose I've got some infinite line L, and I've got a normal vector n sub L, and I'm just going to call it n in the rest of this example. And this is, the slides are pointing out, this also applies in any other number of dimensions. One of the reasons I like normal vectors is because if I have a linear inequality, I can pull the normal vector just directly out of the equation. So we saw earlier we had that negative x plus 3y is less than or equal to 0. If I just yank out the coefficients from this, then I get the normal vector. So that's one reason that we should like normal vectors. I can compute them really easily from a linear inequality. So that's one reason they're convenient. And then we now know a little bit more about projections. Suppose that I have some vector that points in some arbitrary direction, whether or not it's parallel to my line, but I want to lock it into my line. I want a vector that points parallel to my line. Well, what I could do is I could compute a certain projection, and I could use that. Now, what I actually want to achieve here is projecting v onto the line. But I don't have a vector that's parallel to the line. And notwithstanding that I could compute one from the normal vector with more work, I could actually use the normal vector to figure this out. So I know the normal vector is perpendicular to the line. Therefore, if I were to compute the component of v in the direction of the normal vector, and then just subtract that off of v, whatever I'm left over with has to be parallel to the line, because I deleted all of the component of v that was perpendicular to the line. So I get this. V minus the projection of v onto the normal vector will give me a vector parallel to the line. Now, again, the slides are pointing out, you could argue that if you just get a vector parallel to the line and project onto that, you'd save some work. But how are you going to get that vector? You already have the normal vector, and you'd need to use the normal vector to get this other vector that you might be able to use. And moreover, this is fine if I'm working in 2D, because there's only one, the line is only in one direction, so I only need one vector to be parallel to the line. If I'm working in 3D, a plane has one normal vector, but I would need to have two vectors in the plane if I want to project something onto the plane that way. So the normal vector is great because in any number of dimensions, it is the only thing I need to represent the component of a particular vector that is orthogonal to the plane or whatever, the hyperplane that I'm working with. So that's one advantage of normal vectors that isn't as obvious in 2 dimensions. In the case where I've defined my half space this way, with a less than or equal to sign, basically in this format, so normal vector dot x is less than or equal to something, then the normal vector will point outwards. So it will point away from my half space. If I adopt that convention, and we'll see in the next lecture that that's a good convention to adopt because we like inequalities that look like this with a less than or equal to sign. If I adopt that convention, I can now use the normal vector and dot products to figure out whether any particular vector points into, so that would be like this direction or that direction, points into or out of, which would be like this, my half space. And the way I would do that is by examining the dot product. So often the reason we want to do this is because we want to ask whether a point is inside or outside. The way we would ask if a point is inside or outside, using the notation I'm about to use, is here's a point out here called P. What I do is I find some point on the line. Now the normal vector is the same no matter where I am on the line, but I'll choose this point here because it fits in with the rest of my diagram. So I choose a point on the line and I choose a point P, and then I draw the vector from Q to P. So I would call this, we'll call this vector V, and V equals, if we allow ourselves to do arithmetic involving points, V equals P minus Q. So I end up with all these vectors. And I want to ask the question, does this vector point out of or into my half space? Or does it point parallel to the boundary? And I can do that by computing the dot product with the normal vector. By a property that we may know, if I have two vectors, and so we'll use u and v for this. Actually, no, that should be fine. We'll use u and v for this example. If I have two vectors and I look at the minimum angle between them, and when I say minimum angle, I mean you have two vectors. There are lots of angles you can make between them. There's this angle here. There's also this this maximum angle, I guess, on the outside. I mean the inside angle, the minimum angle between them. If the minimum angle between them is less than 90 degrees, then you can expect that u dot v is positive. If the minimum angle between them is equal to 90 degrees, so let's see if I can actually draw a right angle on the screen. If the minimum angle is equal to 90 degrees, you can expect that u dot v, predictably in this case, I guess, this is a fact probably you already know, that it equals 0. And if the minimum angle, finally, if the minimum angle between them is greater than 90 degrees, so there's u, there's v, then we get u dot v is less than 0, then it's negative. And the way I like to think about these three cases is, okay, so obviously u and v in this example don't point in the same direction. They're not parallel. But they do, broadly speaking, they do point in basically like the same general direction. So they're within 90 degrees of each other, which means they're both, if I move along u or I move along v, I'm moving broadly in the same general direction. Here, u and v have completely different directions, and here, in a sense, they sort of have opposite directions. If I walk along v, I'm walking away from the direction of u, and vice versa. So that's how I characterize this relationship of dot products. I can use the same thing for the issue of vectors and normal vectors and half spaces. If v, because I know that my normal vector points away from, it points outside of the half space, if n dot v is positive, that means v points out. If n dot u is negative, as would be the case here, then u points in to the half space.